We have briefly discussed PHYS theory of ferromagnetism in the previous video, and we have introduced these 1 over chi 0 b and theta in order to express our result. If you remember, 1 over chi was written in this form. So I forgot to add these constants, so these are given by these equations. So finally, let's talk about ferrimagnetic materials. So they are called ferrites. Ferrites are ferrimagnetic oxides. They are very good electrical insulators. Since they're good insulators, they can be used for high frequency applications. And because when we have a high frequency AC field, this cannot produce eddy currents that will cause heating in the system. So they're good for that. They're soft magnets, high permeability and high saturation magnetization. They're used in induction coils operating at high frequencies since they can avoid eddy currents. Now we have cubic ferrites in the form MoFe2O3, where M is manganese 2 plus, nickel 2 plus, iron 2 plus, cobalt 2 plus, or magnesium 2 plus. For example, we have nickel ferrite, nickel oxide Fe2O3, FeO Fe2O3, that's magnetite or lodestone. Here we have iron in divalent and trivalent states, Fe2 plus and Fe3 plus mixed. So the conduction mechanism is electron hopping. They crystallize in the spinel structure where the oxygen atoms form an FCC lattice. The tetrahedrally coordinated sites are A sites, octahedrally coordinated sites are B sites, and as you can see here, we have a tetrahedrally coordinated A site and octahedrally coordinated B site. We also have hexagonal ferrites, for example, barium oxide 6Fe2O3. These are widely used as permanent magnets, and they're good for their cheap processing possibility. Another family of ferrimagnetic oxides is garnets. These are in the form 3M2O3 5Fe2O3, where M is yttrium, gadolinium, or lithium. This is different from the other ferrites because the all cations are trivalent, so there is no electron hopping mechanism and the resistivity is extremely high. Therefore, they're useful in very high frequency applications such as microwave applications. So if we substitute the iron with aluminum or gadolinium, the compensation point, saturation magnetization, anisotropy, and the lattice constant can all be tuned. Finally, I would like to talk about another important family of materials called half metals or half metallic antiferromagnets. These are insulators for one spin subband and conductors for the other. A good example is chromium oxide. It is possible because the Fermi level crosses only one spin subband but not the other spin subband. So they have only integer Bohr magnetons per unit cell. When we pass current through this half metal, because one spin subband is completely rejected, we get 100% spin polarized electrons emerging from the half metal. So this basically summarizes the ferrimagnetic materials, ferrites, cubic ferrites, and hexagonal ferrites, and as well as garnets that find applications in high frequency and very high frequency processes.